This is the module of Intech's Hit the Ground Running training program related to MagnaCore hollow bar micropiles. Here's the presentation outline. The presentation will cover the system application and background, the system components and options, system installation, and system design. Application discussion and background. MagnaCore hollow bar micropiles are simply a specific type of micropile installation. The element ultimately consists of a small diameter grout column with steel reinforcing. The micropile elements serve to take a shallow foundation level load and transmit it through a weak or sensitive material to bear on something that is strong enough to bear the load. These elements are typically frictional elements engaging the soils with the outside diameter of the grout column. The thing that is unique about hollow bar micropiles is the one-pass installation method, where the hollow steel tube used to drill the hole for the micropile is disconnected from the drill string and remains in place as the element reinforcement. Other names for hollow bar micropiles are self-drilling anchor, injection bore anchors, and hollow bar anchors. Hollow bar is used in a number of applications such as new construction, retrofit, earth retention and slope stabilization, and tunneling. Some of the biggest advantages of using hollow bar in a project are when there are difficult soil conditions like collapsible soils that don't allow for open hole drilling. This is because the method of installation is able to maintain a grout head which resists hole collapse. An additional benefit of the system is the ability to hammer through the drill string through tough cobbles and gravels, and it's even able to penetrate to create a rock socket into bedrock. Finally, the system is relatively low vibration, has options for limited access, and is able to have galvanization and other methods of corrosion protection applied. The final benefit of the system is the labor and material cost. This is compared to a conventional micropile installation. There are several methods of micropile installation that exist, a few of which include advancing casing ahead of the hammer to keep the pile cavity from collapsing. In these scenarios, you advance the casing, drill a little bit, add more casing, drill a little bit more, and so on until you have to get to the end of the hole. So it takes quite a bit of time, effort, and labor to install a conventional micropile with this method. Whereas for our method of hollow bar installation, the material for reinforcing costs a little bit more, but the savings can be realized in the significantly less labor required to get it installed. The one-pass method is significantly faster, allowing for more piles being installed on a site. System components and options. This is a breakdown of the individual pieces of a finished hollow bar micropile element. The first breakout includes the hex nuts and termination plate, the final injection grout, coupler, and drill bit. The second breakout includes the soil cement grout body, the hollow bar tube sections, and centralizers which hold the bar in the center of the cavity. So a little bit more about the bar. The bar is continuously threaded steel tube. The threads are typically left-handed threaded. The bar is usually shipped in 3-meter sections, but this can be cut into smaller sections for low headroom type installation. MagnaCore is regularly tested for the cross-sectional area, thickness, tensile strength, and yield strength. We also contract out third-party testing to make sure that what you get on site is good or better than what you order. There are typically two styles of hollow bar, namely T-thread and R-thread. R-thread stands for rope thread, and T-thread stands for trapezoidal thread. These designations describe the outer profile of the thread. So this is how the naming convention breaks down. For example, for the name R32S, it has 3 parts. The first part is the letter designation of the bar, so rope or trapezoidal thread. It will have either a T or an R here. The second part of the name will be the outside diameter of the bar in millimeters, so in this case it is a 32 millimeter outside diameter bar. The third part is the hole modifier, which refers to the hole size. The R-thread naming conventions we currently carry are R32, R38, and R51. For our second type of bar, the first part is the letter designation of the bar. For this instance, it will have a T for trapezoidal. The second part of the name will be the outside diameter of the bar, which is 40 millimeters. The third part is the hole modifier, which refers to the hole size. In this case, it's a 20 millimeter inside diameter. These are the current variations of T-thread bar we currently carry. Note the hole modifier for this style is denoted as the inside diameter of the hole. At the end of the day, it is most important to consider the specific engineering properties of the bars from the specific supplier you are getting them from. We generally have the strongest bars in each line in the market, so make sure you consider a smaller bar size compared to our competitors. For instance, it is not uncommon that our R38 bar can outperform T40 bars from other suppliers. So the next component we're going to talk about is the couplers. These are internally threaded sections of tube that connect consecutive sections of bar. There are also gaskets on the inside that engage with the end of the bar to seal the internal hollow section of the coupler. This is to keep the grout fluids from going between the threads and squirting onto the installation crew during pile advancement. The coupler sections are designed and tested to verify they are higher strength than the bar itself. The third component to go over is the bit. The bits are heavy steel components that get threaded onto the end of the bar. There are multiple styles of bits that can be selected based on the anticipated soil conditions. The first one at the top is the button bit. This bit is good for pulverizing bedrock for rock sockets of substantial length. The second style that we typically carry is the crosscut bit, which is good for dense or stiff profiles and even some moderate rock socket lengths. The last style we carry is the clay bit, which is good for clays and softer soils that don't have gravels or sands. There are other types of options that we can obtain, so if there's a specific style that you're familiar with that you would prefer, please feel free to let us know. It is important to understand that each of the styles of bit have ports to allow for grout to flow through them. This is important and an important key to installation, that you always have to be flowing fluid through the bit during advancement, otherwise the bit can plug up. Always remember to flow before you go. The termination assembly consists of a few pieces and is the last component we're going to discuss. The termination assembly consists of a bearing plate with a hole and a few hex nuts. These plates are designed to be large enough to structurally be able to transfer the project loads with the pile cap. Once the design length of the pile has been achieved, the nuts and plates are assembled and any excess bars cut off. This assembly is then typically cast into a footing or pile cap. System installation. So another necessary component for system installation is a grout plant. This system takes cement particles and water, combines them very intensely using the colloidal mixer, and pumps the grout through the system all the way down to the bit. An important key is to make sure that you always have enough cement to finish an element. You don't want to be going to the store for extra cement with wet grout in the tanks. So as an overview of the system setup, I wanted to show this diagram of the moving pieces in the system. This slide specifically demonstrates how the pieces go together for an excavator-mounted installation setup. The drill runs off of hydraulics, so it can either be run off the excavator if the excavator has sufficient pressure and flow to meet the needs of the drill. Otherwise, an external power pack can be used as a supplement to smaller equipment or equipment that doesn't have hydraulics capabilities. The second setup is for a skid steer mounted setup. Similar to before, these can be run off smaller pieces of equipment, but if you need extra pressure and flow, a hydraulic power pack can also be used. And finally, we also have a man-portable drill system that can be moved by hand. There are some limits to the bar this one can install, and the specific drill specs should be checked. So this is a breakdown of everything you'd need for element installation. You need a drill size for the element to be installed, equipment to position the drill over the hole, such as an excavator, skid steer, or dolly, a supply of hydraulic fluid with sufficient pressure and flow, grout, and hollow bar anchor materials. There are a few major components that are included on each drill that should be noted. The first is the place the grout goes through the drill. Ultimately, the grout will need to go through the hollow tube of the hollow bar, so the grout hose will connect to the drill in some place that allows for it to flow out of the striker bar. The second item are the grease ports that allow for lubrication of the drill. The third item is the striker bar. This is an item that allows the drill to connect to the hollow bar. You can either use a shank that has the thread pattern of the bar you are installing or use an adapter. It should be noted that using an adapter for a hole size that is very large compared to the bar can lead to issues during installation. These slides will demonstrate the general steps for element installation. The first step is to install the lead section. The lead section consists of a bit, the first section of bar, and a coupler to attach to the drill. For clarity, I have omitted the drill above. So the first step to advancing is to start pumping grout. While you're pumping grout, you apply crowd and torque. It is also possible to use a thinner grout than the design mix. We call this the flushing grout. It can go as thin as water, but less cement results in less fluid density, which can cause hole collapse. We will also have to displace this grout at the end of the element installation. So when you're drilling, someone should always be looking to verify that grout is flowing out of the hole. If there's no grout return, it's important to assess the reason. Another thing to note, the hole created by the system is taken to be the diameter of the bit. Since we're pumping under pressure, the grout flows into the void space of the soils. This is especially advantageous in sands and results in much higher engagement with the soils. After each section of bar is advanced nearly all the way into the ground, it is good practice to plunge the hole 3 to 5 times. We've been on projects where the contractor didn't do this and it resulted in poor pile performance. So after you're done plunging, you can disconnect the coupler and add another bar section. You can then advance the system, making sure to pump grout before advancing the steel. Another feature of hollow bar drills is they're able to apply a hammering action. This action can help penetrate dense, cobbly, gravelly soils, and also penetrate into bedrock. The vibration helps advance the pile through this dense layer. Also, don't forget to plunge the hole. So now you just repeat this process until your design depth is achieved. At this point, we'll say that we achieved our design depth. The hole that has been created is full of thinner flushing grout, so it is necessary to displace this material with structural grout. If the hole was drilled with structural grout the entire way, this step isn't necessary. You can see here the structural grout has filled in the cavity of the hole, which is the diameter of the bit. At this point, it is necessary to plunge the hole just as before. Now add the termination components per the design. The designer of the pile cap will designate the elevation the plate should be at. The nut should allow for ease of adjustability of the plate. Finally, the termination gets cast into the pile cap. System design. Alright, it's important to note that the things discussed in this presentation are for informational purposes only, and this presentation shouldn't be used to design an element. There's a lot of great information out there, and these are some references we use to validate some of our designs. So with geostructural solutions, there's a few things to consider. First, I'll go through the major principles for the geotechnical capacity. The geotechnical capacity is comprised of two things, the skin friction and end bearing. The skin friction, or side friction, is generally taken to be the surface area of the sides of the grout column diameter. So we would take this area, which is a function of the diameter of the bit, and multiply that by the bond strength. There's also a factor of safety applied to this bond strength, so it can be compared to a design load. This area times the strength results in a resisting load capacity. So with geotechnical systems, there are typically a few layers of soils and/or rock. Each of these layers has a section of cylindrical area that passes through them. It is intuitive that the density or stiffness of various soils results in varying amounts of resistance friction. For example, a soft clay probably won't resist a load as much as intact limestone. So with that friction resistance equation before, and knowing how much cylinder passes through each zone, we can calculate how much skin friction capacity can be counted on for each layer. An important note, there is typically a length we disregard at the top for undocumented fills, active zones for wet and dry conditions, and other cases of soils that shouldn't be counted on for resistance. The design methodologies listed before typically have a more in-depth description of what to use for an unbonded length. So the check we do on the system is to determine if the capacities of each layer are greater than the applied load. If there is more capacity than load, the system is okay. If there is not enough resistance, the length of the pile or the diameter should be increased, or even the number of piers can be increased to decrease the total amount of load on each element in a system. So another type of geotechnical capacity that can be used is the end-bearing capacity. However, as these elements are relatively narrow in the context of geotechnical engineering, this is typically disregarded unless it is in bedrock, and the bedrock is quality rock that has been cored and tested. These values are what we typically use for the ultimate grout-to-ground bond for the soil. A conventional gravity grout system is type A. A hollow bar system, type E, can be seen to achieve higher values of bond strength based on being installed with pressurized grout. As you can see here, on the left are some elements that were installed as solid bar. These elements are smooth-sided. Then the next 3 on the right are hollow bar elements. Based on the pressurized grout and plunging, it creates a very ribbed profile of the grout, which allows for more surface area. In this manner, our elements typically perform better than what we initially design. So these sets of equations represent the structural checks we do for an applied load. These checks are compression and tension. As you can see, for a compression load, the capacity is shared by both the grout and the steel. For tension, however, the only term that is used for supporting the loads is the steel, so the steel is the limiting component for structural support in tension. This is because concrete doesn't do very well in tension. And if any microcracks were to form, the grout would become disengaged at that point. The only thing transferring the loads is the steel. So these equations are relatively simple, but have a few nuances. The safety factors are different from one another, and there are different factors to use based on the methodology you choose to use for design. Another key principle is related to strain compatibility. We could use really high yield strength of the bar, however, the grout will likely fail at the strain required to fully engage the steel yield strength. For that reason, per AASHTO, we usually use a reduced yield strength of the bar. The only way to check these elements is with a load test. Typically, as long as end bearing is disregarded in the element design, it is typically possible to test these elements in either compression or tension. This is up to the discretion of those involved in the project, though. Main takeaways. Here's a breakdown of the main takeaways for hollow bar anchors. Hollow bar anchors can be used in new construction, retrofit, and active and passive lateral support. They are a great alternative in collapsible soil profiles compared to conventional micropiles that require casing. The labor savings of installation typically offsets material costs that would be required for a conventional micropile that requires casing. The hollow bar components are typically comprised of hollow bar sections. The system components are typically comprised of the thread bar, couplers, bits, and termination. There are generally 2 styles of hollow bar, rope and trapezoidal thread. For system installation, a lead section is started with a bit and is advanced, adding couplers and extensions as necessary to achieve a design length. There should be constant grout flow and return of grout out of the hole during installation. Between each extension and upon pile completion, you should plunge the hole 3 to 5 times and even up to 10 times at the end before terminating the pile. For system design, most of the time friction governs the geotechnical design. Structural design is different for tension and compression.